Okay, in this problem, we have the bottom of a large theater screen is 15 feet above your eye level, and the top of the screen is 50 feet above your eye level. Assume you walk away from the screen perpendicular to the screen at the rate of 3 feet per second. While looking at the screen, what is the rate of the change of the viewing angle theta when you are 30 feet from the wall on which the screen hangs, assuming the floor is flat? Okay, so we've got a little picture here to show what we're working with there. I'm going to draw a separate triangle over here. Okay, and then also the right triangle there. Okay, so this is a right triangle. Okay, so they're saying this is theta. This distance right here is 15 feet, and then this distance is 50 feet. Okay, so what we want to do is try to find a relating equation. Let's go ahead and put x down here for this. It looks like we're probably going to use tangent because we have the opposite and the adjacent, but that only works with a right triangle. Okay, so what I'm going to do is split this thing up into two different thetas. I'm going to call this one theta 1, and I'm going to call this one here theta 2. Okay, so you can see that the difference between theta 1 and theta 2, if we subtract them, you'll get theta. So I can say that theta is equal to theta 1 minus theta 2. Okay, now given theta 1 and theta 2 both are representative of right triangles, okay, because they both go down to here. This one goes all the way up to the top line, and this one goes to the bottom line. Okay, so what that does is allow us to use the tangent function. So we can say that tangent of theta 1 is equal to, that's opposite over adjacent. So here's theta 1. So it's this whole triangle here. So opposite is 50, adjacent is x. So 50 over x. Okay, if we solve that for theta 1, we get theta 1 is equal to inverse tangent of 50 over x. Okay, likewise, we can do the theta 2 the same way. So we have tangent of theta 2 is equal to, okay, this is this little triangle here, still a right triangle. Adjacent or opposite over adjacent is 15 over x. So 15 over x. And if we solve that for theta 2, we get inverse tangent of 15 over x. Okay, so given that we know that theta is equal to theta 1 minus theta 2, we've solved these for theta 1 and theta 2. So I can say that theta is equal to tangent inverse of 50 over x minus tangent inverse of 15 over x. Okay, that's my relating equation. Okay, so we're dealing with related rates, so I'm going to have to take the derivative of this thing. So we're going to have to take the derivative of this inverse both of these inverse tangent functions. So over here to the side, I will write, let me write that in a different color. I will write the formulas, the formula for taking the derivative of an inverse tangent function. Okay, so d over dx of tangent inverse, and we'll do a over x. The reason I'm doing a over x is because, well, look what we're dealing with. We have a number over x. Okay, so that will give you negative a over x squared plus a squared. Okay, so that's the formula for these. So the a on this one is 50, and the x is x. Okay, so we're going to do this related rates. We're going to do this with respect to time. So the derivative of theta with respect to time is d theta over dt equals, okay, let's take this one, that's this formula over here, 50 for a. Okay, so that's negative 50 over x squared plus 50 squared. And that's going to be multiplied by dx dt. This is a related rate, so we put the dx dt on the outside when because we're taking derivative with respect to x, or the derivative of x with respect to t, excuse me. Okay, so for this one, minus, and we do the same thing, except it's 15 for a, so 15, and that's negative 15, excuse me, over x squared plus 15 squared. And this is also dx over dt. Okay, So we're looking for, the final thing we're looking for is what is d theta dt? What is the change of the angle? Okay, so that's the question. You can see it right here. What is the rate of change at the viewing angle? So we're looking for d theta dt. So that means we need to plug in values for all this stuff here. Okay, so let's go see what x is, and let's go see what dx dt is, looking at the problem. Okay, so it says when you are 30 feet from the wall. Okay, so that's x equals 30 feet. Okay, that's one of the things that we're going to plug in down here. Okay, and then you're moving away from the screen. If you're moving away from the screen, this is the x. That means the x is increasing. We're moving away from the screen here. So that's our dx dt at a rate of 3 feet per second. Okay, so dx dt is equal to 3 feet per second. Okay, so that gives us those two unknowns. Now it's just a matter of plugging them in and getting our answer. Okay, so we get d theta dt is equal to negative 50 over 30 squared plus 50 squared. And then dx dt is 3. And then, okay, we have a minus and a minus, so I'm just going to put a plus 15 over 30 squared plus 15 squared, also times 3. Okay, now if you work all this out, just stick those numbers in the calculator real quick, you're going to get negative 0.004, and that is radians per second. Okay, and that is your answer.